Okay, so as I said, it's my really great pleasure to introduce Nicolas Stier, that I've been knowing for a very long time. While he was some kind of intern in Rennes, at INRIA in Rennes. So working on something very different. So Nicolas is a very bright guy, having worked on so many different things and very efficiently each time. So, and I always try to invite him to be a keynote speaker when I can, because he is one of the greatest speakers that I know. So Nicolas is from Argentina. He got his PhD from the Operations Research Center at the MIT, and then became an associate professor at the Business School of Columbia. So I know that he went back to Argentina, to Ditela University in Buenos Aires before going back to the US and joining Facebook. So as I said, he has worked on many different things. So he currently works on statistics, economics, game theory, mechanism design, algorithm, machine learning, computational social science, and which shows his very broad range of expertise. So he's now a director at Facebook Core Data Science. And I'm really proud to have him presenting a part of his work at GCon right now. So, Nicolas, the screen is yours.
Thank you for the introduction. Yeah, so I remember those times in Rennes, in France, and thank you guys for giving me the opportunity to go there, work with you, and that was really a nice way to get introduced in many of the things I'm going to be speaking about today. So certainly I owe you a lot for giving me that opportunity. So yeah, so my plan today is to talk about pacing equilibria, which is a concept I'll introduce today, but the more general idea is to talk a little about modeling for high-tech industry, where we need to create models for different reasons. And I'll talk a little about how these models are used and the consequences of doing this modeling. I'm going to be presenting maybe some ideas coming from 3 of the papers we wrote. And in the first slide, I included co-authors that contributed a lot to these papers. So I'm just presenting this, but this is work from many people, what I'm going to be speaking about today. Oops, let me see if I can control PowerPoint. Here we go. No. So I work in a team at Facebook called Core Data Science. We are an applied science team. So the whole idea is to try to bridge the gap between academia, academic science, research, and some product teams in the company. So what we try to do is we try to be informed and contribute about many areas of research, and then try to see how we can apply that research into some product work and try to improve the way they make decisions, the strategies, the algorithms, etc. And vice versa, we try to listen very carefully about the problems that product teams have, and then try to do research on that, and then speak about that in academic conferences. Also, we can be working with other academicians, other people in other companies to try to advance some interesting questions that can be answered through research to try to advance the field. And Bruno mentioned a few. Some of the fields that we are interested at include operations research, algorithms, optimization, game theory, more generally economics, statistics, machine learning, and social science. So some of the common things we work on that are interesting right now, like first, like marketplaces, like Facebook, you can look at Facebook ads as a marketplace, but it's not the only type of marketplace that you can relate Facebook to. Facebook, and I mean Facebook as a company, like there are other apps like Instagram, WhatsApp, and Messenger that are part of the company. So if you think of Facebook as an application now, if you think about feed is a place where people write posts, and then basically when other viewers come to Facebook feed, we render a ranked list of posts where people come and can see these posts and interact with them. So if we think of this, it's also a two-sided market, and you can equate that to a marketplace. And therefore, there are many questions about what's the best way to do it, how to effectively rank, how to control the two sides of the market, etc. So many of these themes will apply there. On top of that, there are also many other marketplaces at Facebook. So first, there is a peer-to-peer marketplace, like a Craigslist type of marketplace in which people can buy and sell items. There is a jobs marketplace, and there is also now shops where people can actually buy and sell in platform or link into outside platforms. So there are many places in which like the marketplace modeling or market modeling more in general would make sense, and that's a lot of what we do. But through that, also, there are many relations to other techniques that then allow you to understand these marketplaces. So for example, how you can experiment when you have a two-sided market. If you have treatments on one side or the other, that will have network effects or consequences on the other. So the way you experiment can allow you, for example, to be very efficient in the experimentation, or maybe you need to do something later on to reduce the variance so you can have a compact experiment that doesn't run for a long time. So there are many people thinking about these things to try to do that. On top of this, ranking is a big thing. So when you have to sort big lists, for example, in feed, you have to feed some type of value model that will allow you to then rank things in the right order. And how do you learn the right value model? So again, either we go back to experimentation, we use other machine learning techniques to be able to do that. And then after you did all that, then you still want to control the aspect of two sides of the market or other aspects about trade-off of different metrics and multi-objective optimization there. So that's kind of in a minute, more or less what we do. And I'm going to focus in this talk on the marketplace issues, specifically on the ad side, but you can take a step back and we can discuss some of those things in the question at the time in which we do questions. Well, I want to give him like my position in this industrial lab. I want to use the chance to speak to you about the relations between practice and theory, given that I'm interested in academic work and proving theorems, but at the same time, I'm interested in how that can influence product decisions. Okay. So the practical goal of the talk is modeling. So modeling is simply that you take a very complex, dynamic, practical problem, and what you want to do is you want to abstract away the most simple, relevant things that you can to make a model that you can analyze either mathematically or computationally. There's no surprise to any of you about this, so I'll continue. Now, if you have a model, you have to develop a methodology that can allow you to solve the model, so you can say something about that. And that's not necessarily easy in practice. Like some models to be able to solve, it need to be very small, or sometimes you solve a model, but you have some unknown parameters they need to calibrate, and it's not clear how to do that. And many of the theoretical papers that we can write, sometimes in conference or in academia, they stop there. They don't tell you how to deploy the model in practice. But if we are hoping to use this in product, we have to do the last mile and then deploy it in practice. So questions are to do how to do that. So after you have a model, like why do you use the model to start with? I mean, there are many ways in which a model can be used. One of them is to understand really the world, to ask what if type of questions and to answer counterfactual questions about something. And that can allow you to set strategy, to design a product. Sometimes you haven't even started the product and you want to understand what are the right design decisions. So that's why you may create a model. If you have a model, you can solve it, then you can change some underlying parameter of the model or some other like element of what you have in the process and run it again, and that will give you the what if question that you're looking for. If you have a product already exists and you have a model of it, then you can compare reality to your model and then try to make them as accurate as possible. Another way you can use a model is to guide the operations of that. So for example, if you have a ranking and you have a model that will tell you how to rank, you can solve the model and then the output of the model is going to be the ranking. So that's the most straightforward way to do things. The problem is sometimes that some of the models that one works with are very sophisticated and maybe cannot run them online to then be able to inform a product decision. In those cases, what you can do is you can design heuristics or you can design other methods that are faster and keep the model to get a benchmark. In that way, then you can run your quick heuristic, run the model offline now and compare the model to the quick heuristic to the model to see whether you should improve the heuristic or you're okay. when you analyze the whole thing offline. In terms of being able to solve, I think one of the ideas I want to get across here today is that sometimes it'd be nice and kind of as a research direction to do more work understanding how we can solve compact versions of a big model that will represent still reality. And I think many of us have worked on things like that in many settings, but one area in which I haven't seen a lot done, so I think it's a good opportunity, is in game theory. So in game theory, say you have a very large game. Think of a large marketplace like the Facebook auction, in which you have many advertisers that are submitting ads to the system, and then there are many auctions being run day to day. If you create a model of that, which is what I'm going to be speaking about today, what is a good way to then condense a very small model for this, for which we can prove guarantees about the equilibrium you can compute afterwards, and what are these guarantees and how we can do it. So I'm going to mention, so that paper that is listed there is an attempt to do that. It's a first attempt. So I mean, I'm hoping that more people are going to be working on areas like that, because I think that can be very relevant to practice, since you may use this type of game theoretical model to understand reality for these type of marketplaces. So it'd be nice to have more tools at our disposal so we can solve things that are relevant and then give us guarantees about how these solutions may compare to the practical models that are much larger. And then about the accuracy, there are many papers that my team and many other teams in the world are working on about how to best calibrate models, how to be sample efficient, try to run a few experiments, but not too many, and combine maybe simulation with experimentation to try to do the best you can. Some of these papers I mentioned there use Bayesian optimization as the underlying technique to then do the right exploitation to learn the right parameters for the right model. I'm not going to be focusing about that in this talk, but I want to at least mention that because that's an important and crucial element that will allow you to close the cycle between the question you had, the model you create, how to solve it, how to calibrate it, and then give the feedback about what's the insight you may get from that model that you produced. And then on the top line there, it says modeling. There are a few examples of different marketplaces or different situations that we work on about modeling that. And there are many other papers because there are many other situations also that people looked at. So that's my quick intro, and maybe it's a good time to stop in case somebody has a quick question, but otherwise I'll go on. Otherwise, I'll keep 10 minutes at the end for questions also, so in case we want to have a longer discussion there. Okay, so let's focus on marketplaces. So I'm going to be talking about specifically the ads marketplace at Facebook. And I want to create a model of that to try to inform some of the decisions that happen in that marketplace, for the simple reason that it's not clear how to fit some parameters. In particular, when you look at the sequential auction system, like the Facebook ads, the advertisers that come to the market have to tell us many things, but at least two that are very important. One is a parameter that applies to every auction, which is how much they're willing to pay if they win an item in the auction. You know, for example, they say for every click that the Facebook can get for the advertiser is willing to pay, say, whatever, 5 cents. Fine, I mean, that's a number, and this is a number that applies for every auction, and every auction happens every time a user loads a feed. So it's okay, they are willing to pay 5 cents. That's perfect. But on top of that, an advertiser may have a budget. Maybe they want to spend more than so much money per day. Notice that this is per day and not per auction. And this is a way to control the budget. Typically, there is a marketing manager in the companies that have advertising, and the marketing manager may have some budget they have to manage between different platforms for different days, for different campaigns, etc. So they will have a budget. And the question is how to go from a budget that is per day to a max bid that is per auction. So these two numbers may be aligned or may not be aligned. And when they're not aligned, the problem we get is that the person may end up spending all the budget in a few minutes. And if an advertiser has some money that they think are going to be spending for a day, they wouldn't like it to spend that in a few minutes. They probably want to expose that kind of idea in the ad to as many people as possible of different backgrounds, etc. So the word can get out about the product they are trying to market and advertise. So the main question I want to focus on today in this context is how to make these campaigns in a way that makes sense so the budgets are aligned with the max bids in every auction that they run. And so you can think of these kind of marketplaces like this is a sequential market in which I'll explain a little more, but there are big auctions being run one after the other. And the auctions, think of a second price auction, which is the closest to what we do, but it's multi-item, so it's not really second price. But you run the auction and then that gives rise of the price. These are called CPMs or CPCs. This is cost per impression or cost per click. And then out of this auction, we get the winning ad, which is the one that gets shown on the feed of some user. We have the code, so we could try to simulate everything, right? So we have all the auctions. We can try to inject some like simulated traffic and then run this through the actual code and do it. But think that there are millions of auctions that happen like all the time, and that's a lot. So if you have to simulate everything, that's a ton of work for understanding what's going on. So ideally, what we'd like to get a handle on some of the issues I mentioned earlier about experimentation, calibration, etc., is that we like to have a system that you can kind of feed some of the main statistics about like who's bidding in these auction markets and try to get from there some idea of what the CPMs, the CPCs, who will win, other metrics and other statistics out of the auction in a condensed way. So think of this as taking a step back and instead of looking at the auction market, auction per auction, try to look at that as a marketplace. So what we came up with are these two papers that look at what we call pacing equilibria. Where pacing here is the word I haven't mentioned yet, is basically the mechanism that will allow us to move the bids in a way that are compatible with the budgets, as I was explaining earlier. So think of pacing as a coefficient that you can tune, and as you tune it, you will be making that max bid compatible to budget. And we need to learn that pacing multiplier. I'll tell you a little more about how we do it in practice. So in practice, we have this pacing process that is done, and I'll tell you about that. What I'm talking about here is I want to create an abstraction, which is this game between advertisers where the participants, which the advertisers, they're the players of the game, have to submit their pacing, their pacing multiplier. And at equilibrium, hopefully, this is going to model what happens in the actual auction market. That's what I want. So we have a first paper about that, which is we do it with the second price auction, with a single slot. That's a modeling abstraction that is aligned with what Facebook does in practice. And then as a follow-up, and this is more as a thought process, we went to say, well, what happens if we replace the second price auction by a first price auction, which is something that hasn't traditionally been used in industry, although Yahoo was the first one that was doing auctions in industry, and they started with the first price auction, but then switched to the second price auction like soon later because of oscillations and instability of first price. So we thought about like replacing second price with first price and wrote a paper about that to try to understand the characteristics. And around the time we were writing the paper, many providers, auction providers, including Google display ads, switched from second price to first price. So there must be something there. So if many of the biggest platforms in the world are switching from second to first price, again, after having left it in the 90s, so maybe there are some good properties, and that's exactly why we try to explore that. We try to explore some of these properties in these papers, because like we all know that the first price auction is not incentive compatible and has some problems, but this is not when you look at it from the perspective of sequential auctions that are being run one after the other. And on top of that, you embed that in this type of pacing mechanisms that will allow the system to do well. So what are the properties of first price compared to second price in this much more complicated setting? So that's what we look at in that paper. And then on top of that, we also look at these abstraction ideas I mentioned earlier, because at the end of the day, if you have a really big auction market that you want to solve, it's really hard to solve. So what are ways in which we can make it small, solve the small version of it, and then try to lift it up to the original marketplace and try to get some idea of how good the solutions coming from the small marketplace are as you try to project them into the big one. So that's the last paper there that I mentioned. So I don't think I'll have time to go very deep in all these directions, but at least I want to mention them in somewhat detail at the beginning, so also get a flavor of what we're doing, so then you can go and look at these papers if you're interested. But let me use my time then to describe some of these directions, so you have a little more context here. And then we can go a little deeper in the 10 minutes of questions at the end, depending on the interest of you guys. Okay, so some of the concepts I plan to discuss. I'll talk a little about Facebook auction markets, so you have some context about where this is coming from and therefore placing equilibria. I think the interesting handle coming from theory is all these competitive equilibrium or Fisher markets that are the type of modeling abstractions that we are going to be using to look at these things. I mentioned first price auctions and abstractions already, and some of these to try to connect it to practice. We do a few computational studies to understand really, besides what theory can say, what happens when I run this through the type of data, type of auctions that we have in practice to understand, how good or bad some of these things may be. So to set ideas, let me tell you what the auction market at Facebook is. So basically we have advertisers, which you can see here in the center of the screen. So you may have a fashion brand, we have an online retailer, a game app. They all try to run ads on the platform. And the platform is typically composed of different participants that come to a platform, open the feed, and they have some characteristics. So here I'm focusing on gender and age, but there are more characteristics that the user may have. So now the advertisers will set a few parameters when they create a campaign, and the campaign is created in advance. So you create a campaign through a UI or through an API, and then the campaign is sitting on Facebook servers that is ready to be run, but it's not an online interaction. You create it in advance. So you create a campaign, you say, as I said earlier, the max bid and the budget. On top of that, also you say who you're interested in showing the ad to. So for example, the fashion brand may select for their ads only female users. And the online retailer, in my example here, will select everybody. And the game app may select people in their early 20s that they want to address with their advertiser. So it gives you this idea of this bipartite graph in which there is an edge if that advertiser is interested in that user. Now, when a user comes at some point, say in this case, this female of 24 years old comes to the platform, opens the feed, that triggers an auction. The auction is run online when the person opens the feed, and we have a few milliseconds to run the auction. This is something happening in the Facebook servers. So what happens at Facebook servers then is we know that this user came to Facebook and wants a feed. You're going to be running an auction, so you need to retrieve all the ads that target a person like that, run an auction between them. So that's basically a competition through the max bids that we talked about earlier. And then the winner, the one that bids the most, is going to place the ad in that feed and is going to pay the second price. And then you kind of repeat that because there are multiple slots in a feed. But I'm not going to be focusing on that in this talk. Okay, so that's the process that happens online. And that's a screen that you can see is the UI where somebody comes and creates a campaign. You can see the budget there. You can see the bid amount there. Also, you have to choose your objective. The objective, maybe they want the people to watch a video, or you want the people to install an app on their phones, or you want people to see an impression or click on an ad. So people will say what, or the advertisers will say what objective they have, and then the platform will measure that and give some statistics back to the advertiser so they can optimize the campaign. So the key thing here is that the advertiser is not interacting with the auction system online, in the sense that the advertiser in advance will create these campaigns, and then Facebook itself will run the auctions. So what we call this is a proxy bidder. So Facebook writes code that acts on behalf of the advertiser in the auction system. So basically, the advertiser tells the proxy bidder, which is code run by Facebook on behalf of the advertiser, how much they want to spend. Notice that the proxy bidder is something that can be changed as many times as you want. So the advertiser has a handle to an API And the advertiser can write a code or a bot that will query the proxy bidder often and then adjust the bid as they want. So the proxy bidder should actually behave as the advertiser, so should encode in a way the best incentives of the advertiser, because the advertiser can always like override it by like programming a bot that will say something new every time to try to adjust it in the best way possible. So what we'd like is the proxy bidder to take the perspective of the advertiser. If you think about the game, the proxy bidder should behave as the advertiser in all these gaming and incentive considerations. And this is where the pacing is coming from. So we want to design the proxy bidder so it optimizes the advertiser utility and not at all Facebook utility or the user's utility. So the advertiser is looking after themselves in this, because this is a game, they want to maximize some metric about the advertising campaign. So let's think now about the timing of this. So in this graph, I have time on the x-axis and I have the price that are paid in the auctions on the y-axis. So as time goes on, imagine that you have this budget that we spoke about, and the advertisers spend the max bid every time an auction happens. So it's a second price bid, so they don't pay the max bid, but they bid the max bid, and then they pay whatever the second bidder bids in that auction. And what will happen is a graph like the one I'm showing you here. So basically, you'll win everything below your max bid, and you don't win anything above your max bid. And then every time an auction happens to be below your max bid, you win, and you spend from your budget until you run out of budget, and then you cannot participate anymore. So notice how, if we run a system like that, you'll have regret at the middle of the day, because you end up bidding. Look at the point that's really close to the max bid that is right in the center of the screen in green. That point has a much higher cost than a point you can see on the right you didn't win that had a much lower price. So you wish you hadn't won that one and you had used your budget to win more of the low price auctions that happen on the right of the screen. So you have regret by using this mechanism because you didn't win what you had hoped to win after the end of the day. So different platforms, if you think about the biggest marketplaces, use different ways to alleviate that concern. And this is what I call pacing, or other people call it throttling as well. So one way to do throttling is to do probabilistic throttling. So you flip a coin every time you participate in an auction, and depending on the outcome of the coin, you either participate or not. And what you need to do then from the platform side is to calibrate the coin, or what's the probability of participation. So some platforms do this. Facebook, like since the beginning of creating the auction system, created this system, and this is much earlier than this paper. They had already done this system before we started working on this paper, that does multiplicative pacing. So basically, if you start from the max bid, which is what I told you earlier, you learn a coefficient, which is a number between 0 and 1, that you multiply the max bid with to get your actual bid. And think of this as trying to compute the best response strategy to the environment. If your max bid was 5 cents, as I mentioned earlier, but that will give you regret, as I showed you in the slide before, well, so what do I need to multiply my max bid with to try to get a lower bid that will have no regret? That's exactly what the game is trying to do, to learn that. Now, because at Facebook, we have this proxy, we can try to learn that on behalf of the advertiser, and the type of algorithms that are used in practice are control algorithms. So what we do, and let me see if I have a slide, no, I don't have a slide like that. What we do is we try to learn the slope of the amount of money that gets spent per hour or per minute. And if you feel that that slope is gonna be exhausting the budget too early or too late, you adjust the slope by controlling the pacing multiplier. So then if you did this right, if you run these control algorithms in the right way, then what you get is for all advertisers, they exhaust the budget right at the end of the day when the new budget comes, renews, because they knew they started. So that way you're always spending the right amount for this auction. And this is what I mentioned at the beginning, which is a way to align the budget and the max bid. But again, Facebook does this through the proxy bidder using control algorithms. What we want to do is we want to take a step back And instead of using control algorithms and dynamics, we want to look at this as a static game where the strategy of the advertiser is just to submit that multiplicative pacing coefficient. And we want to see what's the equilibrium here. Where everybody is playing a best response to what the others are doing, what we get out of that. So the whole area of sequential auctions and all these have been discussed at length in the literature. There are many types of papers. One is about bidder selection, which relates to the throttling and the probabilistic pacing I mentioned earlier, which is to select what participants should be part of every auction. And there are many papers to do that. There are many papers that also look at changing bids, that are some of those that I'm talking about here. And there are a few others that I have mentioned that also look at this type of pacing multiplier type of mechanisms. And then there's so many papers about market approximations, how to compute market equilibria, how to deal with Fisher markets. So that has been like a big area of research, both in the econ side, on the kind of EC algorithmic game theory side, about like combining the ideas coming from econ and algorithms that can compute some of these solutions to these marketplaces. And for anybody who wants to read more, in the bottom line of this slide, I list one expository piece that we wrote with my co-author Christian Kroer to try to summarize what I'm speaking about here in this talk. So anybody who wants to look at that is on my webpage. Okay, so let's focus for a few minutes on this static game of pacing. As I said earlier, then advertisers come to the market, they have bids and budgets, and what they want to submit is a pacing multiplier to maximize their advertiser utility there. So the model is simple. It's a static model with single slot auctions, which are second price. And so let me describe it so we also fix ideas. I don't want to spend that much time on the formalities, but I want you to understand the type of model that we're thinking about. So we have a set of bidders and a set of goods. Bidders have budgets. Also, bidders have valuations, which is a vector that for every good, it tells you how much they value that good. So we can think of that as a matrix, which is what you see on the lower left. For every bidder, they have a valuation for every good, and they have a budget. Okay? And if easier for you, you can represent that as a bipartite graph you see on the lower right. So now that's the basics. This is the input of your game in this case, or your market. Now think of every bidder to come up to this game with a pacing multiplier. The pacing multiplier is going to be a real number between 0 and 1, and the effective bid they're going to come to market with is going to be alpha I, which is their strategic component of how much they're going to reduce the bid, times the valuation. We know it's second price auction, so we know that what people would do naturally would be to bid the valuation. I mean, that's what incentive compatibility said for second price auctions. But because this is a sequential auction, it's not necessarily incentive compatible if you don't do this right. We want to give people the ability to shade the bid and bid something else, which is not the valuation. And what the bidders are going to be choosing is exactly that coefficient. Now, if we play a game, we have to also specify the utility. What's the utility here? The utility is going to be the total value that the bidder may get, which is some of the evaluations, minus the cost they paid to get this valuation out of the auction. Now, the other constraint, and this you can incorporate in the utility or you can take it on the side, is that you need to satisfy your budget constraint. If you exceed the budget, then your utility goes to minus infinity because that's unfeasible. You cannot do that. So quick example, same instance as before. Let's look at the example in the middle that says solution 1. If people come to market with a pacing multiplier equal to 1 and they bid, so basically what happens is that bidder 1 wins both auctions because they have the max bid, because they have the maximum valuation. But the problem is that they exceed the spend. So they exceed the budget because the spend is 0.625, which is bigger than 0.5. And therefore that solution is not feasible in this game. So they cannot bid that. I have a second solution here, which is now the first bidder shades the bid with a coefficient 0.4. And now it is the second bidder who wins the first auction, and the first bidder wins the second auction. And now we have spends that are different. You have the allocation of who wins what that is different. That solution is actually not an equilibrium. So in this case, they have regret and they wish they had shaded the bid in a different way because that wasn't optimal for them. So that way you can define an equilibrium. So this is the definition of an equilibrium. So it's a pacing equilibrium. Now it's a set of pacing multipliers for all bidders such that either you don't necessarily spend the budget, but in which case you don't pace, or if you do pace because the alpha is less than 1, you do it only when you spend the budget. In the sense that, saying this in English, what I'm saying here is that you can only pace, effectively pace, or have an alpha less than 1, only if you're going to be spending your budget. If you don't spend your budget, you have no reason to shade because you still have money to spend at the end of the day. So that's the definition of pacing equilibrium. As in many other settings, an equilibrium will have a kind of two conditions that can happen one or the other. So that's kind of very common in game theory that you have these type of conditions are equilibrium. And then you can come back and compute this pacing equilibrium. And by definition, you would expect that being a second price auction, you'll have many ties in this because you start shading your bid until two things are equal. And that's when you stop shading your bid. And as I was saying, on the lower right of the slide, you can see the equilibrium. And at the equilibrium, you can see how both bidders 1 and 2 at the equilibrium shade the bid in a way that the bid is equal to 0.5. And when you have a mechanism like that, it's not clear from the mechanism how to allocate the winning sides when you have a tie. Because now from the mechanism perspective, both bid the same thing. So what's the allocation of this good to the bidders when they tied? Well, you have to do it in a way that you have to do it very carefully, because if you do it in a way that is not careful, you can force the bidder to exceed the budget. And then you're in trouble because now the bidder will will have utility minus infinity because they spend the budget. So one assumption we are making is that platform knows this, knows the budgets, and therefore is not forcing anybody to get over the budget, to not force anybody to have a minus infinity utility. So if you can do this, then the platform, you can do it in a way so the platform or the user can choose how much they want to win out of these ties, and then everything works fine in that way. Check the time. Okay. Good. So one thing can prove in this setting, I gave you the definition of equilibria by definition. I told you what the pacing equilibrium is. If you embed this in a kind of Nash type of argument, you can prove that this pacing equilibrium I told you about is a mutual best response for all the players. So if you look at the pacing equilibrium that is playing according to the definition I just gave you, you can prove that all the alphas of any player are going to be the best alpha they can select, given that the other players are selecting the pacing equilibrium I told you earlier. So in a way, this is the Nash equilibrium of this game. And some of the details in the proof are, you have to talk about these F's here, which are these fractional allocations I was talking to you about how to preserve budgets. But if you do this properly, you can prove all this. And that's kind of what we do in the paper, is try to give the right argument to be able to prove that this pacing equilibrium is the right concept, because it gives rise to this Nash equilibrium that we wanted for the game that we are playing. Okay, so now that we have a concept of pacing equilibrium, you can take a step back and try to understand, is this the right concept? Is this the right is the right object to try to achieve if you're a platform? So then you can look at global metrics. So the one that makes most sense is advertiser welfare. If you sum the utilities of all the advertisers, you may ask, how good is that? How good is the welfare that you achieve from the outcome of a pacing equilibrium? You can also ask, what's the revenue you achieve from this outcome? And one related concept is that now that you shaded the bids, you can ask, what's the paced welfare, which is the sum of the paced welfares of all the bidders, where the paced welfare is the sum of the alpha I times the VI, where the VI is valuation. And it makes sense to place the welfare, because otherwise advertisers will have to an incentive to really exaggerate on the valuations, because they can claim, hey, if you place this ad in the platform, my utility is going to be huge, because I know that the platform is going to shade it anyway, and I'm not going to be paying that much. So otherwise I can kind of maybe get the platform to publish more of my ads by exaggerating my value. So in that sense, the paid welfare is going to be more immune to these things, as opposed to welfare, which is going to be, possibly gamed by the advertisers because they are exaggerating something. So we look at these metrics, and this slide compares some of the papers in the area. Given the time I have, please focus on the column on the right, which is our paper. And what we show is that an equilibrium always exists. This is not at all trivial to show. It's complex because of these ties I talked to you about earlier. So because of these ties, there are many discontinuities at equilibrium, so we cannot use the usual fixed point arguments to prove that equilibrium exists. So it's a ton of work to prove it, but actually you can prove it through some smoothing arguments. Uniqueness, unfortunately, equilibrium are not unique, so you cannot rely on that. So you have to go through equilibrium selection somehow, because you have many equilibria for an instance. In the worst case, I mean, in practice, you may have unique equilibrium. We look at that through computations, but we have examples where there is more than one equilibrium. About welfare, there are large differences between different equilibria. So if you have more than one equilibrium for one instance, what you get is that different equilibria may be very different. And then another question is how to compute it. So we provide an algorithm that is based on integer programming to compute it, but that's very inefficient. So it's not a good algorithm in the sense that you cannot scale it to really large instances, which is why we look at abstractions, as I mentioned earlier. Okay, quick things. I'm gonna go quickly now just to show you a few concepts, but then move on. So multiplicity of equilibria, we have very simple instances like this one, in which you have a disjunction about how to do something, and two ways to do things, about like selecting things like that or like that, are indeed equilibria. So, and the two are very different. If you look at this slide, you can see how the span in the first one is 100 for the last player, whereas in the second equilibrium is 1. So you have a large difference of span between different equilibria, depending which allocation you take. All this is at equilibrium, so it's about equilibrium selection. The question is that this does happen often in practice. Another usual algorithm, another point, a usual algorithm to compute equilibrium is to iterate best responses, and that doesn't work. Here's an example where things cycle, so you go back to the original bits when you do that. And again, you may ask how often this happens in practice for the type of instances that we may run. So ultimately, these conditions I showed you earlier about equilibria, you can encode everything as inequalities using both continuous and integer variables. So the set of equilibria here can be written as the solution to this to the solution of this big polytope using integer variables. So I'm not going to describe the equations anyway, but on the left, there are some complementarity conditions that describe the spacing equilibrium condition in which you have one or the other. And the block of equations on the right describes that this is a comprised auction, and this is how you set the prices in this. But if you solve this all together, if you find the solution to this system, you get an equilibrium. So that's some handle to solve it, and that's what we used. But unfortunately, this doesn't scale. So if you have like more than tens of auctions and tens of bidders, the problem is that you cannot solve this in any realistic way, which is why we try to connect it to these Fisher markets and competitive equilibria literature, and try to understand relations between pacing equilibria and this type of Fisher markets, which will give us a handle to then compute something in a more efficient way. Actually, Fisher markets can be solved using polynomial algorithms. I mean, they may not be the most efficient because they are quartic polynomials, but they're still polynomial. Whereas this is known that this is NP hard, so we cannot solve these equilibria efficiently in practice, in theory, because of NP hardness. So one thing I want to mention quickly is on some of the empirical insights that you may get by solving these equilibria for realistic instances. So we took some data inspired from real auctions to try to understand the type of markets we have in terms of the bipartite graphs and the type of bids that people have, and then artificially create instances that we can run to understand what's going on. So we compute that, we solve for equilibria, we solve for all solutions of this mixed integer problem. And we find that most often there is a single equilibrium, and when there are many, if there are two or more, usually when you take the best and the worst, the gap between them is very narrow. So the type of like theoretical worst cases I'm telling you that happens, in theory, they don't happen that often in practice, so we haven't seen that. So in a way, that gives us some relief that you can actually solve these things and they work out fine when you look at realistic instances. Another thing that we did is to basically go back to the actual process, which has a sequential auctions and time, and try to use our static equilibrium to feed a dynamic system that does the control type of thing that I mentioned earlier that happens in practice. And quickly here, what you can see from this graph quickly is that on the y-axis in this graph, you have regret. So low regret means that you are getting close to equilibria. So the four solutions on the left are solutions in which you start from a fixed amount. Fixed amount can be either random or can be fixed, like start with a pacing multiplier of 1, or close to 0, or in the middle. And the right panel here in this picture is the one in which you start from the solution of the pacing equilibrium program. And you can see how regret is much lower when you start from the right place, because then the control algorithm can learn faster what's the right pacing multiplier in practice. So that's a nice conclusion, because it gives validity to all this and gives you a way to make this operational, because you can use now the solution of the pacing equilibrium to feed your dynamic system, which is the one that is used in practice in actuality to tell you what to do when you want to get closer to equilibrium. Okay, so let me see. I want to kind of stop soon so we have time for questions, and we have 9 minutes to go. Bruno, what do you want me to do? Do you want me to talk for a minute or two about some of the ideas for abstractions? Do you want me to stop now and give some conclusions and then?
Go ahead, in 2 minutes, it's not a problem at all.
2 minutes, all right. So I'll do quickly the abstractions to give you an idea of what this is, and then I stop for questions and we can go deeper in any of these directions, depending on the questions. So as I mentioned, right now we understand the context of this. We cannot solve really large instances because of this mixed integer equilibrium. Even if we go through the Fisher market abstraction, the problem is that you still need to solve something which is quartic. This is a snapshot of the paper that provides an algorithm for this type of Fisher markets and market equilibria. And you can see how this is n to a fourth. So now we're talking about millions or billions of auctions, right? So this is a huge market. So n to a billion to a fourth is something we cannot hope to even compute. So that gives validity to this idea of let's try to see what we can do to try to represent this big market as a small market and see whether we can provide any type of worst case guarantee about the solution that we can compute as you lift it to the original market. So what we did, and there is a paper about that, is you take the original marketplace, which you can abstract as this bipartite graph we mentioned earlier, that can encode as a pacing equilibrium or a Fisher market, as we mentioned during the talk. And you can make it compact in some ways. There are many algorithms to make something compact. You can take the case centers using some embedding, so to try to take all the bidders and the users that are kind of close by in a space using some features. And then you can project your graph into a smaller graph. Okay, so now you have a smaller graph. The smaller graph is something you know how to solve, so you can compute a market equilibria for the smaller graph. So that gives you an assignment of who gets to buy what and at what prices. Now, because you had the assignment of the abstraction to a compact representation of the abstraction, you can try to lift it up now and go back to the original but large marketplace. And you have to make decisions about how to do this. So for example, you're gonna, like you may solve a smaller problem for any one of the small abstractions that you use to encode the big market into small market. And as you go back, you're gonna be assigning also like a matching between the two sides of the markets in this bipartite graph and a price for each of these transactions in this graph. And then you get your allocation and your prices for the larger market. Now, in this kind of transition of steps that I told you earlier, how much did you lose? Like, all this is nice, but if it gives you something that is not very close to the actual equilibrium for the regional market, it's useless. So the question is, can you prove anything here? And we managed to prove something. I don't know if the best thing that you can prove, but at least it's some initial results in this area. And I invite more people to think about these problems because I feel they're really interesting and very useful for what one needs to do in practice. So what we worked on is, if you look at the evaluation matrix, which is a large matrix, and you try to make it more compact by taking a small rank for the evaluation or using these ideas of using k-means or k-center to try to make it compact with, like, to make it block diagonal in a way you're doing that. Then you have the original valuation matrix, and you have the compact valuation matrix, which represents a small market. What we can prove is that if the distance between these two matrices now in some space is not too large, then the equilibrium that the result from the two valuation matrices is also not very different from each other. So that gives you a handle to understand, really, depending how close you can come up with your block diagonal matrix or your low rank approximation matrix, then that gives you an idea of how close the equilibrium is going to be compared to the original equilibrium. And we do some computations here. We have a few graphs that, as you make the thing more sparse, because you're compacting it more, you lose some on some of the metrics that you care about that describe equilibria, but you don't lose too much. So basically, as you make it more compact and more compact, you are still in some type of approximate market equilibrium that makes sense and gives you some idea of what you want to compute. Okay, let me stop now. I know there was much more material and you have time to introduce. So let me stop with some open questions. So for other people that may be interested in looking at this. So we proved some ideas about convergence and complexity for some of these equilibria. So I think it'll be important to do more there to prove, like, whether we can approximate some of these equilibria in a better way. So being NP hard, is not the best of the world, but still, that doesn't preclude that there may be some nice approximations to compute approximate equilibria, or even to compute, like, other objects that are close to equilibria in some ways. So I think there is space to do more. There is space to do more on the dynamics. The models that we talked about are static, and they look at this concept of equilibria when players select only once the pacing multiplier or some other participation characteristics. But in practice, all the things happen over time. So there are some papers that look at the dynamics. There is this really nice paper by Balseiro and Gur that looks at that. And they have a flavor of control algorithms when you look at dynamics, but embedding that in a game setting would be super interesting. Further relations to market equilibria. It's a huge literature. Many people work on market equilibria, on definitions and algorithms and connections to real world. So I think to connect things more between market equilibria and some of these actual markets that happen in practice is a very interesting idea, because you cannot really model everything that happens in practice. So having a good tool set that will allow you to abstract the right things will be great. In terms of our own paper, relations to other second stage games. So we look at single slot second price auction, but in practice there are multiple slots, there are reserve prices, things are much more complicated than what our paper models. So I think there is space to do more in some of these areas. And finally, I think it's interesting to continue to exploit relations to other systems in which you have constrained resources, and you have a centralized mechanisms that needs to, give away the resources in the right way. And you have examples like bond auctions, supply function equilibria are kind of other areas of work that relate to this, but they have maybe solved the market in a different way, and understanding why in high tech we run these sequential auctions, where in bond markets they have these centralized bond auctions that are different, why one works in one setting and one doesn't work in the other. I think it's interesting to understand more about the interplay between different industries and what type of mechanisms they have devised to basically distribute their scarce resources. Let me stop now. Thank you very much. Questions? I'm happy to stay for questions.
Many thanks, Nico. So that was very, very interesting, and it's a very nice mixture of theory and practice. So first, I have one or two questions, but I would like first to receive questions from the audience.
Yeah, maybe I can start.
Patrick.
Hi, Nico. Nice to see you.
Patrick, how are you?
Thanks for the very nice talk. Just to be sure, I understood when you define equilibria, you mean exposed equilibrium, right? That the equilibrium you would have reached if you had known everything that.
Yes, so this is a static full information game, so already knows everything. So think of this as a game like that. So everybody knows already else, they know all the evaluations, etc. All they need to submit is this alpha, and there's no uncertainty here. So everything is there.
So if you want to apply it in practice, you would assume that the next day will be somehow similar to today, and you compute the equilibrium on the last day's data.
That being static means that this is played only once, I guess, from the abstraction of the game. So basically, I assume I know everything because the proxy bidder would know the evaluations and would know the bids and the budgets. I use that to compute the equilibria, and
because it does not depend on the user behavior. Because I'm thinking of like AdWord auction, when the auction is run only when somebody searches a term. Here, it's not the same. It's not when some users do something that the auction occurs.
No, if you think about the static model, because I have the goods already there, they are part of the game, is that I'm already forecasting who's gonna show up in the day. When I say who, I'm not talking about the individual users, but say I have segments of users. I can predict how many will come in every segment. And may not be super accurate, but I have good ideas and statistics about how many people will show up for different segments. So now it's the start of the day. I can forecast all that. That's the static game that we have here. So we have all the users are known, all the goods are known. Sorry, I should have said all the advertisers are known, all the goods are known, all the utilities are known, the budgets, etc. So now we can play the game in which everybody has to submit the alphas.
Yeah. Okay.
So that's abstraction. In some of the other papers I mentioned, and you can go back to the table I mentioned earlier when I was describing some of the literature, they don't consider that. They consider this to be a dynamic game, or they consider this to be a static game, but there is uncertainty in terms of there is the evaluation is drawn from a distribution as is usually done in auctions, and they look at this type of setting. That turns out to be an easier setting to solve because things are continuous. When you have a continuous distribution, you take the evaluation from. And kind of the difficulty we have to deal with is all the things are discrete because I start with a concrete instance that I need to solve. And that's what gives rise to all these ties that I have to deal with. But that's exactly the setting in which we are at, is at the beginning of the day, you know the advertisers, you have a good idea of who's going to show up for the day. So all this is kind of known. I mean, there's some certainty, but it's kind of known.
Yeah, okay, see. Thanks.
Yeah, of course. More questions?
Okay, Nicolas. Okay, Anna, go ahead.
I'm sorry.
Too many questions.
I thought that AdWords were divided to two types. There are the AdWords that have some valuation that you can't really grasp, like publicizing an idea, and then there is the online shopping where you have a very substantial return per click.
Yep.
So it would seem to me that the first type would be right to work on a budget, but the first type might be better off working on a per click valuation. If I have twice as much customers, I will sell twice as much, make twice as much. So
yeah, you're totally right.
There are two models required.
Well, I mean, you're totally right. So there are two types of advertisers. There are some that want to do marketing. They want to get the brand out. And for them, they have a budget. All they want to do is they want people to see their impressions or their videos because that's brand. And they have what's called the direct advertisers that want to maybe sell something. So they want people to click to buy something on the platform. App installs is a good example of this. People want, if they install an app on your phone and the app costs maybe $1 to install, and in the ad, if they can get a new person to install the app and pay whatever, say up to 50 cents for that, they know that they have 50 cents of difference in their pocket. So they don't have really a budget. As many as you can give them for 50 cents, each of them is going to be 50 cents for them to win. So there is no real budget, which is, as you said. So different advertisers will produce different type of campaigns, and the budgets and the max bids will be very different for the reasons you said. So for the first type of advertisers, maybe they have a fixed budget, and the bid, they don't care that much as long as they show the ads. So many people, I didn't mention this in the talk, but many people don't know their max bid. They just have no idea. They only come to Facebook and says, I want to spend $10 a day, and I have no idea what the max bid is. So what we do in those cases, you can leave the max bid empty. And what we do is we start from a really large max bid, and we let the control algorithm that learns spacing to find the right max bid to get that budget and leave it there. Now, for the others that do the more like the type of advertising in which the utilities are really important, and this is what leads that, like the app installs and the clicks, etc., that I mentioned. In those cases, typically people have a very large budget. They don't care about the budget. What they say, and you can turn pacing off, by the way. So it's not that pacing is on by the, like it's the only way to have it on. You can say, hey, so give me as many as you can. I have no budget. For each one you give me, I make $50. So I don't have a limit to how many you want to give me. So for that max bid, give me as many. So also people may create a complex topology of campaigns. You may say, look, I know that the majority of my users are going to be in a given country, say whatever, the US, for example, and therefore I want to sell in the US, and the max bid for the US is going to be, this number. But I know that usually the people that buy me most often are going to be people in their 20s. So I want to create another campaign on the same product for people in their 20s, and for them, I'm maybe willing to bid more because I know they're more likely to buy my product. So people create many campaigns and manage that to try to get their ads to the right people, and then maximize their ROI, their return on investment on the advertising dollars. So many of the big brands have campaign managers that are really tweaking these systems, and they may have many software engineers that are building bots to try to do this even dynamically as the campaign progresses over the day. So there's a big ecosystem of not only the advertisers, but companies that provide services to advertisers to improve the bidding strategies for all these reasons. And don't forget, let me add one more thing. Don't forget that in all I said, we take the perspective of the advertisers wanting to maximize the utility, which is what I said earlier, which is how much value we get out of the system minus the cost that we pay out of this. Some advertisers may have a different utility in their minds, and therefore our automatic system may not apply to them. And for them, it makes sense to have a bot that does something else, because like what we do automatically is not what they want to do. So for them, like, the right thing to do would be to, the default option is not the right one for them, and therefore they want to tweak the API to bid something else that makes sense for them. And companies offer that service if an advertiser doesn't want to do it in-house. Does that make sense as an answer?
Yes, and it's even more interesting because it means that you can clearly distinguish the two types of bidders, the budget bidders and the per-click bidders. And I was wondering if it's not too rude and too impossible. Is it possible to release some data about the shape of the distribution of valuations. For example, I would be very happy to know that it is distributed by a Pareto distribution, because it will assure what I think. It would be very sad if it's normally distributed.
I understand that. I sympathize, but I cannot release data like this. So all the data is released goes to like a big approval process. But
of course,
yeah.
of course.
I
don't think anyone
I
has
can
ever
see.
released any
I can see if
data.
anything was open source in the past or any other data is available already. I can look for that, and if there is any, I'm happy to share with you.
Not necessarily with me. I think it would be
Yeah. Well, with you, with the academic community. Yeah, totally, with the academic community. Yes.
Jon, you had a question.
Yeah, right, Nicolas. So thank you very much for the presentation. Really gives some insight in how these things work. So amazing. So I'm wondering about. I mean, as you said, you're trying to combine the theory which is out there with your actual problem that you have at Facebook, and so I'm wondering what is the next step. I mean, you're still finding solution to these auctions, and at a certain point it has to go in the production process of Facebook. So how do you convince now, to make this the primary kind of auction that you have developed? So are you giving data out there? Are you showing the comparison? So what is needed to convince people? I mean, I would expect that the people at this point, they are not the experts in auctions. So how can you state that you are doing better? So I'm wondering.
That's a fantastic question. I mean, that's my day to day, exactly what you ask. And yeah, it's super interesting. This paper is special in the way that we're not trying to propose a way to improve a method in practice, but we're trying to explain why a method in practice has been used in terms of I think one of the main questions, if you think about the mechanism that is used at Facebook, is that not all industry use the same type of shading mechanism as I described today. Other people use the other probabilistic shading, the probabilistic throttling, as opposed to multivariate pacing. And one of the questions that people had is like, okay, so we do this, but why do we do this? Is it better to do this than to do this other thing? And what are the relations between this and that? Or on the second price versus first price question is, okay, we do second price and we want to continue doing second price, but it's a valid question to say, what would happen if we ever decided to do first price? So these are the type of things that we can answer with this type of papers. But in the sense, as you ask, it's not the usual type of endeavor in which I did the paper to convince a product team that there's a better way to do something. In this case, it wasn't, because the team had already decided how they want to do something, and I was trying to explain ex post as opposed to ex ante. But the most common setting is that some product has some idea about doing something, and then we try to go in and then help them make a decision based on some, theory, model, etc. And in those cases, there are several difficulties. One is the timeline, that the engineering teams will have a time in which they want to start writing code. And you cannot say, okay, I'll be back next summer, and then after I have the papers, we can discuss how to best do it. They have their timeline, and you have maybe a month or two, and then they will start coding. And if you have an answer, great, you try to convince them. If you don't have an answer, they'll do the best they can out of what they can, think as the best possibility. So typically what happens is you use all the insights coming from academia, theory, etc., and you try to come up with some idea. And maybe you didn't have time to prove all the final theorems for that area, but you have an idea of what seems to work. So then you give that advice that coming from your understanding, that's the best you can do, or those are the ideas you have. And then after the engineers start writing code, maybe you try to take a little more time to prove the right theorems, and therefore you can have validity to your opinion you gave to them earlier. But that's in terms of what we do. In terms of how to convince them, I think that's a really relevant question. I think it's important that you don't work on the side, right? So it's not that people tell me a question and then I disappear and come back a month later saying, okay, I solved your question, this is the answer. So things even from the engineering side, like the questions evolve over the time, the interest of what they want to implement also evolve all the time. So I think it's important to develop a trust relationship with them and work close to them. So, you know, they feel, we all feel we're part of the same team trying to solve the problem and try to come up with the best solution or best algorithm possible for that problem. So that way, you know, we keep going to the same meetings, discussing the advances every week, etc., until, you know, maybe we have some answer that makes sense, and then they go on and implement that. And then, you know, it's not the end, because then when they implement that something, then maybe they run an experiment or we test the code, and then you go back to say, you know, the experiment said this, is that compatible with what we thought it was going to happen or not? I mean, like, for example, if you have stopped in this paper and you say, well, there are multiple equilibria, maybe you say it's a problem. But then if you run this on experiments, you see that, yeah, maybe in theory there are multiple equilibria, in practice there is a single one. So that turns out not to be a problem. So then you have to keep iterating and try to keep improving and refining on some of the ideas that are coming from the initial theorems, and try to scope them in a way that gives more insight to the teams working on that, and you keep iterating. And at some point, maybe the question changes and there is a new product, and then you switch to that question. But those are people who already work with you, so they know that, you know, that you're also trying to solve their problems together, and that way, you know, things end up working out nicely that way.
Yeah. So right, it's a long-term process, as you said, and then trust-based, right? That you can make your point, right? That you understand their problems, right? And then that those problems are actually also yours, right? So in this way, then, right, a consensus can be found, it seems like. Yeah.
Yep, that's exactly
okay.
Right.
Yeah, thank you very much. Very, very interesting.
But I think, yeah, for me also, it's interesting to give talks like this, because then by telling you guys, I assume most of you are kind of on the academic side. Maybe there are somebody from companies also in this presentation, but also it's nice, like, you are more aware of my day-to-day, and then we can work on some of these problems together, and then bring that back to, you know, these discussions, because at the end also I'm reading your papers, like the papers we all publish. And that way there's a nice feedback loop between, at the end of the day, product and people doing research in things that are related to some of these products.
Yeah. Yeah, right. So that's why it's very important to have this kind of exchange here. Yeah. You're very much right.
Thanks. So, is there another question from the audience? So, for me, I have a very general question. At the beginning, you were saying that the auction, it was starting with the first price auction, and we went to second price auction, and then you were saying that we are coming back to first price, right? So I was not aware of that. So have you some examples, real life example of?
Yeah. So some of the display advertising marketplaces went back to first price. Yeah, if you check the paper of the first price auction paper, I gave you a link in the abstract. You'll see the references there and quotes from different people explaining why they did it and what's going on. So yes, there are some of the smaller also advertisers or platforms that do advertising that also did it, but it's not as significant as somebody like Google. And it's not all Google, it's not AdWords, it's just some area of display ads and that did that. But yeah, it's interesting, and we're trying to also, at the time in which we're working on this, we're trying to understand why we're seeing that in practice. Some things like that were happening. And yeah, what we found in our paper is that there are some good properties of first price when you shade the bids. So it ends up being in practice incentive compatible, and some of the properties that because of which first price auctions were not looked at in the past are not present when you start shading bids and doing other things. So that's why maybe it's interesting to review some of these mechanisms in this light and see, you know, how valid they may be in practice in some platforms.
I was not aware of that, so I have to read your papers. So that's you're good marketing.
Yeah, check the references. So yeah, this is happening not because of our paper. This is happening elsewhere. We just found out at the same time we were writing the paper.
Okay, so we had a lot of questions, but still open to new questions from the audience if someone wants to to ask something. Doesn't look like. Okay, I'm gonna stop.